This is the first video in the series. We're going to, before we talk about any signal processing stuff, we're going to do kind of an overview on complex numbers because these things come up like the whole entire semester, and they're very important, and it's very important to get a good intuition for how they work and what they are, etc. Okay, so the big idea is that there's three forms of complex numbers. The first form is the standard form, then there's the polar form, and then there's a there's exponential form. Okay, we're gonna work our way up to this form, which is the most important, which is what we'll use all the time. But let's start with the standard form. So the standard form is what you're probably used to seeing, a plus bi. A complex number has a real part as well as an imaginary part. The real part has no complex, imaginary number associated with it, and the imaginary part is scaled by an I. We always represent complex numbers on this plane. So this is called the complex plane. Just like the xy plane, we usually have x and y here. With complex numbers, we're going to have the real axis here and the imaginary axis here. So if I wanted to plot a plus bi, what that means is, hey, walk on the real axis a, walk on the imaginary axis b, and go a plus bi right up here. Okay, so that's what this point a plus bi lives right here. Okay, so this is one way of representing a complex number. It's like traditional regular coordinates. Go this way in the x, this way in the y, and get to your point. Okay, polar form as well as exponential form utilizes the idea that you can also represent this number, this complex number, by its magnitude. So how far it is from the origin, in combination with an angle. And we call that angle theta, and we call this magnitude r. Okay, so it's just a different viewpoint. To get to this green point, you could follow the standard way and say, hey, I'm going to move this way to the right and this way up. Or you could say, hey, I'm going to stand here at the center. I'm going to turn a certain angle theta, and I'm going to walk r units. And then you get to that same point. So it's just different ways of saying the same thing. If now we want to find a way of relating a, b, r, and theta, we could use some trigonometry and say that, okay, this side right here is r times the cosine of theta, and this side right here is r times the sine of theta. So in other words, our complex number, instead of a plus bi, a can be replaced with r cosine theta, and b could be replaced with r sine theta. So we would get r cosine theta, right? That's a being replaced, plus b, which is r sine theta, times I. Okay, and we do a little bit of writing. So let me do something real quick. Let me move this guy down a bit so I have some space. Okay, so the standard way of polar is writing it like this. You factor out the r, cosine theta, plus I sine theta. Okay, so it's just another way of writing the same thing in standard form, just using a magnitude r and an angle theta. Okay, now the real important one is the exponential form, which is, hey, it uses an identity called Euler's identity, which says the following, that e to the I theta is cosine of theta plus I sine theta. Okay, and for now, take this for granted. There's a lot of proofs of this identity. One uses like Taylor series and calculus. There's also a nice kind of cool proof that I'll talk about in a little bit. But for now, take this for granted. And then you can see that, okay, over here, you just sub this with e to the I theta. So the exponential form of a complex number is r times e to the I theta. Okay, so these are the three ways of representing complex numbers in the plane. You have standard, you have polar, and you have exponential. Okay, other stuff, good background to know about complex numbers is that if you have a complex number, a plus bi, we have an operation called its conjugate. So let's say our original complex number is x equals a plus bi. We denote x conjugate as a minus bi. So hopefully you've seen that. Okay, it's nice to see what that means in the exponential land of things. And so if your x is a complex exponential, so if your x looks like this, again, this and this are equivalent. They're both just complex numbers. the way you take your conjugate is by negating whatever your angle is up here. So theta would become negative theta. So you get r e to the negative I theta. Okay, this can be seen in many ways, right? If this is a plus bi, then the conjugate, right? So originally our point is a plus bi, and we get to here. The conjugate, oopsies, would be a minus bi. So we would want to go down to here. So as you can see, it has the exact same magnitude. So r is the same, but the angle itself goes from, you know, theta to negative theta. So that's why here, oopsies, here we change our angle, because this is a very important identity to know. What else? Using there's another important thing, using Euler's identity here. Okay, so here's what if I write it for e to the I theta. Now underneath it, I'm gonna write an expression for e to the negative I theta. Okay, or maybe to make it clear, I'll write it e to the I times negative theta. Okay, so how am I going to evaluate that? I'm just going to go up here, and everywhere I see a theta, I'm going to replace it with negative theta. So that becomes cosine of negative theta plus I sine of negative theta. Okay, now keep it's good to know that cosine is an even function. So there's an identity that says cosine of negative x is the same as cosine of x, and sine is an odd function, which means sine of negative x equals negative sine of x. So these are two identities that are helpful. Plugging those in, we can rewrite this whole bottom expression. So I'm going to write e to the I times negative theta. Remember, before it was cosine of negative theta, but that's the same as cosine of theta. And here it was I sine of negative theta, which sine of negative theta is the same as negative sine theta. So this becomes minus I sine theta. Okay, so that's the expression for e to the I negative theta. If I add these two up, notice that plus I sine theta minus I sine theta cancel, and I'm left with e to the I theta plus e to the negative I theta equals 2 cosine theta. And so to solve for cosine theta, I can divide both sides by 2, and then now I have an expression for cosine of theta in terms of, so this takes a real, completely real valued signal, cosine of theta, completely in the real world, and represents it in the imaginary complex world. And this identity is one that's going to be very useful in the future when it comes to, you know, finding Fourier transforms and doing proofs in that sense. Okay, so the last thing, the last thing I kind of want to motivate is why this e to the I theta even makes sense here. Like this, from going from, you know, standard to polar makes sense, right? It's literally like r cosine theta this way, r sine theta this way. It's just trigonometry. But I never really understood for a long time why we use r e to the I theta and why that means anything. So here's kind of the way I like to think about it. I'm going to erase this side right here. Actually, can I undo that? Yeah, okay, I'm going to undo that, and I'm going to put it down here somewhere. So let me do this. Okay, so let's say, okay, we didn't know this. Okay, we're trying to figure out, okay, what could be an expression for e to the ix. Okay, let's say we do know, however, that it is a complex number. So we know e to the ix has something to do with complex numbers, but we don't know exactly what it is. Okay, so for now, let's just write it as some function a of x plus some function b of x times the imaginary part. So this just says, okay, my function, my e to the ix is some complex number. I'm trying to figure out what a and what b are. Okay, well, let's do something. Let's take the derivative of both sides. So here I'm going to note that the derivative with respect to x of e to the ix is going to be I times e to the ix, correct? Which, so let's take the derivative of both sides. We get I times e to the ix. Okay. Now notice that we have I multiplied by e to the ix. Well, I can just sub in what I already know about e. So let me write this a little bit cleaner. Okay. The derivative of e to the ix is I times e to the ix. Okay. Which is equal to I times, well, we know what e to the ix is. It's a sub x plus b of x, sorry, a of x plus b of x times I. If we expand, right, so this whole thing is just e to the ix, because we know that from here. Now if we expand this out, we get I times a of x plus b of x times I squared. I squared is -1, so we get minus b of x. Okay, so we get minus b of x plus I times a of x. Okay, so what we said is the derivative of this guy here, right here, is equal to this guy. So the derivative of a of x plus b of x times I equals that guy. And now notice, can you find any a and b that like make this work? So we're looking for an a such that its derivative, right? We match the real part and we match the imaginary part. So we're looking for an a such that the derivative of a is -b, and a b such that the derivative of b is a. And naturally, that should lead you to sort of think that, okay, my a of x should be cosine theta, and my b of x should be sine theta. And those are the only two functions that will actually make this work, because if you take the derivative of sine of theta, you get straight up cosine theta. And if you take the derivative of theta, if you take the derivative of cosine theta, you get negative sine theta. So that's why now we've solved for a of x and b of x. We can put them back into here, and we see that this identity holds, right? That e to the I something equals cosine of something plus I sine of something. Okay, so I think that's all like the oh, one last thing. Okay, let me scroll down a bit. The kind of geometric view of all of this, which is always good to keep in your head, is that, look, we said that e to the I theta is cosine theta plus I sine theta. Sometimes it can be like hard to see where this cosine and sine is coming from. Here's the way I like to think about it, okay? So e to the I theta means what, right? If I just have e to the I theta, there's an invisible r here, but that r in this case is 1. So this is all radius of 1, which means all of these points on, let me do it in a different color. All of these points on the complex plane are living in a circle of radius 1. That's a terrible circle, but it will have to do. So this is where, let me do it in a different color. Okay, here's where all my points are living. Okay, so if I say, okay, if I choose e to the I pi over 4, well, that's sitting, okay, go pi over 4 degrees. That's where my point is sitting right here. Okay, because it all has a magnitude of 1, right? We're not scaling this at all. Okay, so what does changing theta do? Changing theta just takes a point on this circle here and starts rotating it around and around and around and around. And if we go theta equals pi, we get here. If we go 2 pi, we get all the way around, and so on and so forth. Okay, so now that's what this e to the I theta is. It's going around in a circle. Okay, going around in this circle. So where did the cosine and where did the sine come from? Well, I like to think about it like this. If you were standing right here, so let me put your eye here. How do I draw an eye? Like this, okay? So you're looking at the plane like this, and you're watching this theta change, okay? But you're only looking from this perspective, right? So technically, the point is moving around like this, but you have no perception of depth in this way, right? All you can see is that it goes up and it goes down, and it goes up and it goes down, right? Because you're not seeing it move left to right. So for you, right, it's starting, what does the waveform look like? Well, it starts at 0, right? It goes up, it goes down. And across time, that's what this point is going to look like for you, right? If this axis is time, and this is kind of what you're seeing height-wise, that's what it's going to look like, right? And this is kind of in the I direction, okay? What is this? Well, this is a sine wave, right? This is the graph of sine of theta. Starts off at 0, gets bigger, and then smaller and bigger and smaller, right? Similarly, you probably see where this is going, but if I stand here, let me draw another eye, or whatever you want to call this. If I stand here and look at this point, where does it start? Okay, it starts at a value of 1, and it's going to start to move, but I have no perception of it going this way, right? So all I see really is it starting like here and moving left, right, left, right. I can't see it from a like this perspective, right? So what the graph will look like for me is, if I'm going to draw this graph sideways, here's your time, okay? And it's going to start off up here at 1, right? And it's going to go, down and up and down and up and down. And this graph is exactly a cosine of theta graph, right? Oh, sorry, I shouldn't have put t here. I should put theta here as our axes, but whatever. So this is where the sine and the cosine are coming from. Basically, this one rotation around a circle captures both sines and cosines in its rotation. Okay, so sorry for the long video, but this sort of intuition is very. While I'm giving this outro, I'm also making sure I didn't forget anything huge, but it'll come up in future videos if I did forget it. But this kind of intuition of rotating around a circle and understanding the relationships between these three forms here is very, very important. And it will help you, do proofs better and solve problems better and do well in the course. Okay, thanks for watching.